So today we'll be talking about two topics: writing the equation from a graph and stretching polynomials. So it'll be the end of 8.1.2 and the beginning of 8.1.3. Stretching polynomials. So I'm going to reference 8-31 that has us finding when a certain polynomial is greater than or above the x-axis. So we have different shapes for our polynomials, where we have a cubic that might look like this. We have quartics that can take an M shape, a W shape, a U shape. So we want to see, can we draw these based on what the number line has? So if it's shaded in, it's saying the graph is above the line. And all these open dots are where the x-axis is. So for this first one, I'm thinking it has to start in the lower left to be able to go above the x-axis. But then it stops shading, so I need to be back below the x-axis. And then to be above forever. So I have this cubic shape that works for that one. Moving on to B, it's kind of weird that I'm going to have above, and then I have to quote unquote cross, but then be above again. Well, we did have an option of a double root. Now remember, if we had a double root, it may bounce and maybe go back down through because it doesn't have to be above. So we have this bounce at 0, and then it goes back down through 2. In this one, I have to start above, go through that x-intercept. Now this one, I have to hit this x-intercept, but I can't go back above, so I might have another bounce. So this one maybe takes more of a W shape. And then similar, really what I have to have is these two pieces above. So there's a couple options for this one, but I would say easiest enough to just make an M shape and go from there. So really we're just having you play around with the types of functions. And one of the distinguishing features between an even or odd degree function is what we call the end behaviors. So I'll use that cubic that I had prior to this. So let's say I have something like this. The end behaviors on what is this function doing as it approaches or goes towards infinity. Like there's not any more, there's a common trend that it's just going to follow that trend. So for example, in this cubic, notice that it goes up forever and eventually tends towards positive infinity. And on the left side, it goes towards negative infinity. Well, if you looked at maybe some x to the 5th functions, they can look very cubic-y as well, but they might have some more bumps. They might go boom, 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 boom. But I know it's an x to the 5th for something like this because, again, of those end behaviors. It's going to positive infinity, and it's going to negative infinity. If we look over at our evens, our classic even is a quadratic. We could have an x to the 4th, our quartic, which maybe takes a W shape. But we also said that it could have an M shape. But look at these end behaviors. Unlike these cubics over here in this x to the 5th, this goes down to negative infinity and negative infinity. This goes to positive infinity and positive infinity. So what we notice, or what happens with evens, the end behaviors, I'll write this over here. So even degrees, the end behaviors go the same direction. So they either both open up or they both open down. Where odd degree, like we saw, x to the 3rd, the 3 is odd. So they have opposite end behaviors. That eventually it'll go to positive infinity and eventually go to negative infinity. So just a side note that the book wants us to know that we can categorize these shapes with evens and odd degrees, and that will help us graph some of these. At the end of 8.1.2, we had this 8-33, where it says, choose a couple of these and see if you can actually create a number line game. So what we want to do is start predicting what these graphs will look like. So if I have the factored form here, we want to find those zeros. We want to find the x-intercepts. So I know a 2 will make that set of parentheses 0. Similarly, 3, 4, -5, I'm going to have an x-intercept. Now, I notice, though, that it has that squared. So that's a repeated root. Okay, whenever we have a repeated root, it's going to bounce. So what I want to think of is, well, what's the degree? Is it even or odd? And do I have any bounces? Well, if I were to distribute all this stuff, these are generic rectangles, whatever it is, eventually I'm going to have some x cubed and then plus da, 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 da. So I'm going to have a cubic shape, and this could look many different ways. So since it is a positive cubic starts in the lower left and then ends up in the upper right. So like negative infinity in the lower left and upper is positive infinity. So I do have a bounce though at -5. So I might bounce here and then go through it too. That's one possibility of what this looks like. Now the peaks and valleys could be a little bit higher, a little bit lower, and that depends on the type of function. So if I was doing a number line, I'd have an open dot at 5 because it is equal to there, but we're saying it stayed below. And then at 2, it stays above forever. Similarly, I have a much bigger case here that I want to figure out what the degree is. Well, if I distribute out this, each linear term is going to add 1 to our degree. So that's a degree 1 squared, cubed, and then a quartic. So eventually I'll have some x to the 4th. And those x to the 4th, especially when you have a lot of different x-intercepts, are going to look like W shapes. So I have a 0. Looks like I have a intercept. Oops, planned that out a little wrong here. 0. Looks like I have a -1. I have a +3. And I have a -4 for my intercepts. So again, we want to know that this does open up. It is a positive quartic. And we want to see when it would be above or below. Since these are truly x-intercepts, I have to go through, 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 and through. And then I would just shade wherever I believe that it's above. Well, it's above over here, it's above between here, and it's above to the right over here. So that's how we can make a number line to say, hey, when is this greater than 0? Now moving on, that's eventually what we want to try and see that you can do without your calculator. Obviously, in a situation you may have your calculator, but finding the zeros, like this one's at 1, 0. I'll put a dot there. At -2, put a coordinate there, and at 1, 2, 3, 4. So 4, 1, and -2. And what we want to start seeing is, can I just draw a good sketch of this? I have a note right here, though, that does have a squared, so it is going to bounce. You might want to put a little reminder on there and what the degree is. So similarly as we had just before, we had a quartic that's going to bounce. So we have the end behaviors opening up. It's a W shape, but I have to bounce right there. And then go through. Oh, I messed that up. Hold up a minute. See, I make mistakes too. I bounced on the 2. Wonder why that didn't work. I go through the -2, bounce on the 1, and then through the 4. Okay, so that might be a sketch of it. And what we're going to see is move on to 8.1.3, where we can still do that. Now, if I have the graph of it, maybe I can make the equation, but there's a little added piece to this. So I might make the equation based on the zeros. Notice I have one at -2 here. I have one at 1. So I'm going to have an x plus 2, and I'm going to have an x minus 1. But if I look at that, I might think, well, wait a second, that's just a quadratic, which is true. So there might be a key piece that I'm missing. And the key piece that I'm missing is this. Always be looking for those bounces. We want to see those repeated roots. So I might think the function for this is y equals x plus 2 squared times x minus 1. And it says without a calculator, but I'm kind of curious to see. I'm going to graph it with my calculator and see what happens. And look at this. It has a similar shape, but something's different. That this only goes like a y-intercept of 1, 2, 3, 4, and this has it up at 8. So that's our idea for 8.1.3. That in this case, I can make this graph, but maybe there's a little add-on to this. So we still start the same. We're going to say y equals, in this case, I have just a 0 at 0, and then I have another 0 at 4, so x minus 4, but I do have another bounce. I have x squared. So if I were to graph this, it actually wouldn't, it would look similar, but it's not going to have the same steepness. It's not going to have the same peaks and valleys. So what happened is that there's a stretch, and we have to deal with that. And we're going to deal with it just like we did before when we were given a coordinate. It works as just the same as polynomials as it did with quadratics. So I'm going to put an a value. Now, when I have that a value, I need to know one of the coordinates. So for example, in here, I know one of the coordinates is 2, -6, and that'll be given to you most often. If not, you might have to just estimate like the y-intercept or try and find one that says an exact solution. So I have an x and a y, and I'm going to plug those in. So 6 equals a times 2 squared times 2 minus 4. And we got to show our work for these. So 6 equals, well, this becomes 4 times -2, which would be -8a. So the 4 times the -2 is -8 and an a. I'm going to divide by, oops, sorry, this is a -6. Divide by a -8. And eventually it says a is 3/4. So then I could go in my calculator, maybe graph that, and that is the equation for this one. So I would say my final factored form of this is 3/4. And a lot of times we leave those in factored form, but you could expand that, not too bad. I just wanted to do one example, or one more example that's a little bit bigger. We have a quartic here. I see that I have 4 x-intercepts. So I'd say y equals, I'm just going to start off right off the bat. You might as well, in this case, and if the a value ends up being 1, no big deal. But I get a, I get x plus 3, x plus 1, x minus 2, and x minus 6. They gave me a coordinate of -2, 2. So I plug in my 2. I don't know what a is, but then I go -2 plus 3, and -2 plus 1, and -2 minus 2, and -2 minus 6. So I have 2, a times 1 times -1 times -4 times -8. Okay, so I'd have 2 equals, eventually we get -1, so it's going to be a negative overall. 32, -32a, divided by -32. And that becomes our a value. Our a value in simplified form is -1/16. So always be looking for a stretch. It's really good if you're getting the zeros out of that, but there's probably going to be a stretch factor, and we need to see the work and shown work to see what your a value is. Hopefully this is helping out. Keep up the good work.